Today we start our study of multiple integral. I'm sorry, I can only use the slide to give this lecture because I move into the campus and because the Wi-Fi in the campus is different from the apartment that I live before, so my iPad could not connect to the computer using the campus Wi-Fi, so I have to use the slides to give this lecture, and I will try to fix this problem as quickly as possible so that I can use the iPad to write by hand. Okay, so to study the multiple integral, we firstly study the integrals over rectangles. So firstly, we record that if I is an interval, closed interval, endpoints A and B, then a finite subset P of this interval is called a partition of this I. We require that the subset P containing the endpoints of the interval. So that is if P, because P is a finite subset, suppose P has n plus 1 points, then 2 of the points in P must be the endpoints of the interval. For example, we might assume that x0 is A and xm is B. Okay, so we have n plus 1 points taking from the interval. 2 of the n plus 1 points are the endpoints of the interval I. That is x0 equal A and xm is B. So this is the partition of a closed interval. And a partition of the interval divided the interval into m sub-intervals of the form xi minus 1 xi. Okay, so this is the partition of interval that I believe you encounter this in the study of single variable integral. Okay, now we are studying multi-variable integrals. So suppose we have n intervals ii which endpoints ai and bi, then the Cartesian product, that is i1 close in, this n interval, we're taking the Cartesian product of this n interval I1, I2, in. This is called an n-dimensional rectangle. So Cartesian product means I is an n-dimensional points. The first coordinate of the points, I is a set of n-dimensional points. That is, a point belongs to I if the first coordinate of that point is taken from the first interval I1, and the second point of I, the second coordinate of the points taken from the second interval I2, and the last coordinate of the points is taken from the ith interval in. So such a Cartesian product is called an n-dimensional rectangle. Here we have a picture. So this is a two-dimensional rectangle. Of course, we can also imagine this as an n-dimensional rectangle because in a piece of paper, we could not draw a higher dimensional object. So we can imagine that the horizontal interval is a horizontal segment or horizontal boundary of this rectangle is I1, and the vertical boundary is in. Okay, actually this is a two-dimensional picture, but we can imagine this as an n-dimensional rectangle. Okay, so that is the concept of rectangle. Now the intervals I1, I2, in are called edge of this rectangle. Okay, so and we also define the volume of the rectangle. That is the length of the product of all the length of the edges of the rectangle. That is the product of from I equal to 1 to n bi minus ai. Here bi minus ai is the length of the ith interval ai bi. Okay, so multiplying all the length of the edges, that is ii, we obtain the volume of the rectangle. Of course, this is a natural generalization of the lower dimensional case we know. For example, if n is 1, n is 1, that is a one-dimensional rectangle, that is actually the closed interval. Then the volume is the length of the segment, okay, or the interval. And if n is 2, then this is actually a rectangle. So the volume defined here for n equal to 2 is precisely the area of that rectangle, two-dimensional rectangle. Okay, and if n is 3, that is our usual volume, three-dimensional volume. Okay. Of course, this is the generalization to a higher dimensional case. Okay. Now, suppose I is a rectangle which edges I1, I2, In. For each I1, I2, In are closed intervals. Therefore, we have a partition of the intervals. Okay. So suppose the ith interval II has a partition Pi. Pi is some finite point, finite numbers of points taken from II. Okay, so the Cartesian product of the Pi is called the partition of the rectangle I. Okay, so here we also have a picture. So this is an n-dimensional rectangle. The horizontal, the lower boundary is I1. The left boundary is In. So in I1, we take 1, 2, 3, 4, 5. We take 5 points in I1, which divided I1 into 4 intervals. Okay, and for I2, I3 until In, for example, here In we take 4 points in In, which divide In into 3 intervals. Therefore, all these points, all these including the point inside the rectangle, but I just labeled the point on the left boundary and the lower boundary. We also have the upper boundary and the right boundary, and also the point inside the intersection of all the lines in this picture. All these points altogether there are 20 points, because horizontal direction we have 5 points, vertical direction we have 4 points. Altogether is 20 points. These 20 points, P1 is the partition of I1. P1 is this 5 points, horizontal 5 points, and the Pn is the vertical. Okay, 4 points. Therefore, P1 close P2 close Pn. In the picture I just show you, altogether is 20 points. So these 20 points, are called the partition of the original rectangle. That is this rectangle. So these 20 points determine a partition of our rectangle consisting of 1, 2, 3, 4. 12. Here we have 12 side by side smaller rectangle. Okay, I mean here we have a rectangle, and in I1 we use this 5 point to divide the I1 into 4 rectangle. Or we consider the two-dimensional case, that is n is 2. Then in the for I2 we use these 4 points, divide I2 into 3 intervals. Okay, so in I1 consists of the in union of 4 intervals. I2 is 3. So altogether, all the sub-interval of I1, the Cartesian product, all the Cartesian product of the sub-interval of I1 and the sub-interval of I2 give us a small rectangle. So altogether we have 12 smaller rectangle. 1, 2, 3, 4, 5, 6, 7, 9. Okay. So this is 12 rectangle. So but in notation, we use the P1, P2, Pn are the partition of the edge of the rectangle. So the Cartesian product of P1, here P1 is the horizontal 5 point. P2 are the P2 consists of the 4 vertical points. Therefore, P1 Cartesian product of P2 is precisely all the intersection in this picture. That is 20 points. These 20 points can be identified with the 12 small rectangle side by side here. Okay. Of course, there are more than 12 small rectangle. For example, this is a larger rectangle, but we consider the side by side one, small one. 1, 2, 3, 4. Each row has 4 rectangles. We have 3 rows. Okay. So the point, the key point here is that the point in the Cartesian product of P1 and P2. Naturally, P1 and the Cartesian product of P1 and P2 are the points. That is all the intersection in this picture. Altogether, there are 20 points. But we identified those points which are small rectangle. For example, this rectangle can be identified with the 4 points 1, 2, 3, 4. In this way, the partition of this rectangle can be determined by can be identified with the Cartesian product of the edge I1, I2, In of the original rectangle. Okay, so this is a rectangle partition of the rectangle I, and as I said before, it divided the rectangle I into some sub-rectangle of this form, J1, cross Jn. Okay, so here all the Ji are the small intervals. Here the Ji are small intervals. So of course I use a complete notation, but we don't care about this notation anyway. And as I said, we abusing notation. We denote this rectangle. We said that this small rectangle belongs to the partition P. Okay, that is for the partition of the rectangle P. We mean the Cartesian product of the partition of each edge of the rectangle. This P, the element of this P is not rectangle. The element of P is the points. The points here. That is 20. In this picture, there are 20 points. That is, these 20 points are the element of the partition P. But those points determine the small sub-rectangle of this form. Therefore, we can identify the sub-rectangle in this form J as by element of P. Okay, so this is some abusing notation. This will give some convenience for our later notation. Otherwise, the notation will be much complicated. Okay, so in our notation, we can use the induction to prove this result. That is, the volume of the original rectangle equals the sum of all the sub-rectangle determined by the partition P. For example, in this picture, the original rectangle, that is the largest one, rectangle, the area of this rectangle equals the sum of the 12 sub-rectangle here. Okay, this can be proved using induction, and we will not perform the proof here. I suggest you to do this exercise. Okay, now suppose now f is a bounded function defined on this rectangle, and and we use a partition P. P is a partition of the rectangle I, and J is a sub-rectangle determined taking from the partition P. And for example, in this picture, so this is a J. We have 12 rectangle here. For each rectangle, we take the infiniment of our function f over this sub-rectangle J, denoted by small mjf. And similarly, we take the supplement denoted by capital MJF. Okay, So in some sense, this small mj and the capital mj are the minimum or maximum value of f over g. Of course, this increment and the supplement might not attend. Therefore, they are not actually the minimum and maximum. They should be called infiniment and supplement. Okay, but so we introduce for every subrectangle J, we introduce small mg and capital mg. Okay, then we use the infiniment and to multiply the volume of J. For each rectangle, for each subrectangle J, we computed mg and then multiplying by the volume of J and sum up over all the subrectangle from the partition P. This number is called the lower double sums of our f under the partition P. The function f is given. Using different partition P, you can compute different lower double sums. Okay. Similarly, using the capital mg, using the supplement, you will obtain the upper double sums. Okay. So, given a function and given a partition P, we can introduce the lower sum and the upper sum of our function f related with respect to the partition P. Function f given different partition will give you different lower and the upper sums. Okay.